Welcome to EDU World Space.
For this problem, we are considering an astronaut starting out on Earth, traveling, so this is my little spaceship here, traveling towards Alpha Centauri. I'm just going to represent it as a circle with an alpha inside of it. The distance between Earth and Alpha Centauri is going to be 4 light years, and our astronaut is traveling at 0.8 c. For part A, we're asked, how long does the trip take? How long does the trip take? As measured by a clock on Earth. I'm just going to write according to Earth. So we need to keep in mind here that because the astronaut is traveling at a relativistic speed, there is going to be time dilation. Specifically here, from the point of view of Earth, Alpha Centauri is stationary, and the ship is moving away at 0.8 times the speed of light, 0.8 c. So 0.8 c is the speed that will be measured according to Earth. We know the distance from Earth to Alpha Centauri is 4 light years, so the time is just going to be, according to Earth, the time will be just the distance divided by the speed, which in this case is going to be 4 light years divided by 0.8 c, which gives us a result that it should take 5 years, according to Earth. Now, for part B, we need to consider the astronaut's reference frame. How long is it going to take according to the astronaut? So, what we can do is we can consider that from the astronaut's reference frame, the ship is stationary, and Alpha Centauri is moving as is Earth. So for this, we'll use the equation that t prime equals t minus, it's going to be u x over c squared divided by the square root of 1 minus u over, so that should be u squared over c squared technically here. So the event of arrival, if we imagine the event of arrival in Earth's reference frame, so let's say Earth here, the event of arrival will be taking place at x equals 4 light years. That's the distance. We're just laying x along the distance from Earth, or as the distance from Earth to Alpha Centauri. And it will take, according to Earth, 5 years. So, using the Lorentz transformations, we could transform x to x prime, but that's not really going to matter here. But the Lorentz transformation, plugging everything in, we'll have t is the 5 years. We have u is 0.8, so we'll have 0.8, or u is 0.8 c. So we have 0.8 c times 4 light years. So 4 light years is essentially 4 c times years. Then we have divided by c squared, divided by the square root of, now the 1 minus u squared over c squared, that's just going to be the same thing as 0.8 squared in this case. And that should evaluate to 3. So from the astronaut's point of view, it will take 3 years to arrive at Alpha Centauri. Now for part C, we are asked, what is the distance? So distance according to astronaut. We want to figure out what the distance is in the astronaut's reference frame. So for this, we can use the equations for length dilation, which is that L moving is going to equal L rest times the square root of 1 minus u squared over c squared, which in this case is going to be 4 times the square root of 1 minus 0.8 squared, which is equal to 2.4 light years. Now for part D, we're told that there is a radio signal sent from Earth to the starship every 6 months as measured by a clock on Earth. What is the time interval between reception of one of these signals and reception of the next signal aboard the starship? So let's say we have event 1 taking place. So let's put this down, event 1. Event 1 is the first signal being sent out. Let's say that's at x1 equals 0, and t1 is equal to, let's say the first signal is sent out the 6 months after the ship has left, so t1 is 0.5. Then we have event 2. It's going to be occurring at x1 equals 0, sorry, x2 rather, equals 0, t2 equals 1. Then, in our transformed reference frame, or in the moving reference frame, we'd have t1 prime is going to equal t minus u x over c squared divided by the square root of 1 minus u squared over c squared. So that is going to give us, so we'd have 0.5 minus, that's going to be, so since we have x is just 0 here, we can just ignore that term, or that term, the term being subtracted from t is going to just go to 0. Then it's just going to be 0.5 divided by the square root of 1 minus 0.8 squared, which is going to be calculated off screen here. 1 second. 0.8 squared. It's going to be about 0.83. Then event 2, t2 prime, we'll have 1 divided by the square root of 1 minus 0.8 squared, which is going to give us here about 1.67. So t2 prime minus t1 prime is going to equal 1.67 minus 0.83, which is going to equal, second here, 0.84. Of course, we could also go through and use the time dilation equations directly. So in this case, this is it'll take 0.84 of a year. Doing the translation of that, one moment, so we'd have, or the time difference is 0.84 years. So to get months, let's say delta t months, it's going to equal 0.84 years times 12 months per year, which is going to be 1.84 times 12. One moment. Yes, that is going to be about 10 months. Now, for part E, the question is set up the same way, only rather than having the radio signal being sent from Earth to the starship, the signal is going to be sent from the starship to Earth. But keep in mind that according to the astronaut, so I'll just write down astronaut here. According to the astronaut, he is not moving. He is stationary, and the Earth is moving away at a speed of 0.8 c. Whereas according to the Earth is stationary, and the astronaut is moving away at 0.8 c. So, in the case of the astronaut sending the signals to Earth, the transformation is going to be the exact same. Again, delta t is going to be 10 months because of the symmetry in the situation. Lastly, for part F, we are asked if the wavelength of the radio on Earth, so we have wavelength at rest, is 15 centimeters. We have to figure out to what wavelength must the starship's receiver be tuned. In this case, we'd have the equation, the observed wavelength is going to equal wavelength at rest times the square root of 1 plus the radial velocity away from the signal source, which in this case is just going to be the velocity that we're traveling at. So we have 1 plus u over c divided by 1 minus u over c, which in this case we have 15 times the square root of 1 plus 0.8 divided by 1 minus 0.8. And our result is going to be 45 centimeters. Should have included the 5 centimeters up there, or the centimeters up there. But that is the result. We would need to tune to a wavelength of 45 centimeters.